All right, we're going to talk a little more about electron configuration. And what we're going to talk about are the exceptions to the rule. Okay, we've finished talking. We've done electron configurations for a whole bunch of different elements, but there are several that break the rules. So we have to go back to thinking about Aufbau and what Aufbau means. Aufbau means we're going to fill from the bottom up, because we're going to go to the lowest energy. In our hotel model, that's lowest price. But electrons really want to go lower the energy, the more stable they are. So, as you go up in electron levels, you're gaining more energy. And they want to fill the lower energy. But there are a few exceptions to this rule. Okay? Take chromium, for instance. Chromium has 24 electrons. So if I put his electrons in, wait for it to work, well, maybe, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, the 3D level has more energy than the 4S. So 4S fills first, and then 3D. 21, 22, 23, 24. Okay. However, there is a dirty little secret, because it's actually more stable if this D level is half filled completely than having a completely filled 4S and then these D levels, these 4 with one empty one. So what chromium actually does is it steals that 4S and brings him down here to 3D. So we get a electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Okay? I know that's not very good writing. Here we go. I drew a picture. Right? Not only chromium does this, but you'll notice silver, if we wrote him out conventionally, he would end up 3D. He does the same thing. He steals, so we get 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So that ends up more stable than if it's 4s2, 3d9. Furthermore, we can look. This is a periodic table, and you'll notice that in the bottom of this periodic table, and this is on your periodic tables too, they just don't show up as neatly as they do on here. It says 2892. The 2 refers to the first energy level, 8 in the second energy level, 9 in the third energy level. That's because there's 2 3s2, 3p6, that would be 8, plus 1 in the 3D. So that would be 9 in the third level, 2 in the fourth level. Titanium, same story. 10 in the third level, 11 in the third level. But notice, we switch to 13 in the third level now instead of having 12. And that fourth level drops down to only 1. Back to normal, back to normal, back to normal, back to normal. Exception to the rule. Okay? So if chromium does this and copper does this, does it make sense that some of the other ones would too? And yeah, molybdenum does. Molybdenum also follows that rule. This would be 5s2, 4d, or 5s1, 4d5. The s1 is right here, 5s1, and 4d we've got 4s2 plus 4p6, that's 4p8, plus 5 more electrons, 9, 10, 11, 12, 13. Okay? Notice, it would make sense maybe tungsten would do it. No, tungsten doesn't. It follows the conventional rules. Does silver follow this rule? Yep, silver sure does. And so does gold. Right? But tungsten, for whatever reason, doesn't. We even get something similar happening in the F orbitals. F6 will steal from the S orbital immediately in front of it, which is 6s, and F13 will also. But I'm not going to worry about those. Suffice it to say, the only ones you're going to get asked about would be either chromium or copper. So those are the ones to look out for. All right, see you later.